Okay, good morning. Let's start. Do you have any questions before we start? Okay. So last time, roughly speaking, we were discussing 11.1 intro and 11.2, well, of course, intro for confidence intervals, and 11.2 confidence interval for the mean. Now, the whole idea of confidence intervals are actually pretty easy. Well, not easy, but if you understand the concept of it, then 11.2 and the rest are quite straightforward, trivial even. So actually, the book doesn't spend much materials discussing 11.1, but I want to expand, on the idea of confidence intervals. And it's a bit abstract, but if you get the idea of confidence intervals, then anything following after 11.1 are just applications of this idea, and you'll see that it's very, very straightforward. So before I go into 11.2 and the rest, I still want to expand on the idea of confidence intervals. And as I mentioned before, there are many approaches to confidence intervals. So we introduced the basic ideas of confidence intervals, what it is, what you should watch out for. All right, that's what confidence interval is. Okay, so we discussed what confidence intervals are. Okay, so that's the what that we discussed last time. So today I want to discuss on the how. I want to kind of elaborate on the how. So we want to discuss on the how. Okay, and it's the how that I was talking about. I was referring to that basically there are many approaches. And by approaches, I don't mean like many pivot random variables. Actually, pivot random variable is one single idea. All right. So actually, that's what we'll be focusing on, the pivot random variable approach. There are many other approaches that we do not discuss. For example, the hypothesis testing based confidence intervals and likelihood ratio test based confidence intervals. All right. So the one we focus on the pivot random variable idea. And this is enough. All right. If you get this, I think this is already enough for the chapter. All right. So what's the idea? The idea is that basically, you have, so we have something, right? So the idea is we find a pivot, stat or random variable, whatever, right? Theta hat. Let me say theta hat pivot, for theta. Now, theta hat pivot must satisfy certain conditions, One, it must have known distribution, because if you don't know the distribution, then how can you form a confidence interval? Two, it must not involve any other unknown parameters besides theta. All right. So actually 2 has 2 layers. Theta hat pivot definitely must depend on theta. Otherwise, how do you form the confidence interval? All right. So here, theta hat pivot must depend on theta. All right, implicitly. Otherwise, the whole point of pivoting is meaningless. 3 is basically now we pivot around the known distribution in 1 to find a confidence interval for theta. All right. So the example, right, the prime example you want to keep in mind is x1, xn, iid, normal mu sigma square, right? And here theta is equal to mu. So we are looking for the confidence interval for the mean. If theta equals to sigma squared, then we look for confidence interval for population variances, for example. So we discussed, right, our theta hat pivot or mu hat pivot, if you will, is x bar minus mu divided by sigma over root n. Okay. Now, so let's check, right, that 1 and 2 are satisfied. 1 is satisfied because, right, x bar minus mu divided by sigma over root n is a normal 0, 1. So it has a known distribution. Okay. 2 is satisfied because we assume sigma is known. Now, obviously, right, if we don't assume, so let me put it down here even, right? Sigma known. Of course, this is highly unrealistic, as I mentioned before, and we'll very quickly try to remove this. But demonstrating the idea of pivot random variable, right? Let's not drag this in to begin with. So that's why we assume this is known. So 2 is satisfied. If sigma is unknown, then 2 is not satisfied with. So this, if sigma is unknown, then this is not a pivot random variable, okay, in our definition. 3, right, the act of pivoting is just the act of writing down some probabilistic statement like this. Right, and pivoting means move mu, right, around, so that actually mu becomes, right, the member of the mu is stacked right in between the two left and right random points. And so, right, the act of moving from here to here is the act of pivoting. Okay, and that's it. Once you get that, you get the 1 minus alpha confidence interval. So that's that, right? And if you understand this whole approach, then, like I said, you understand confidence interval as we mean it in this course, and you understand the abstract idea of it. One last thing I want to say, right? This known distribution, you can see that in the flavor of 2 and 3, I guess 2 kind of already mixing into details, but this known distribution, right, should be free of parameters. Yeah, okay, I will. It should be free of parameters, all right? It should be free of unknown parameters because, you know, if it depends on known parameters, it's not that bad. But still, ideally, right, look at the normal 0, 1. Normal 0, 1 is a distribution that does not depend on any unknown parameters. So the typical one, right, that the known distribution that would kind of collapse to will be, like, as I mentioned, standard normal, chi-square, F distribution, and T distribution. You can check that none of this depends on any parameters. I mean, unless you count sample size as a parameter, but sample size is not considered a parameter, okay? Sample size is a sample parameter. It's not a population parameter. All right, Madhav, you want to go over 2 again. So by 2, I just want to highlight how our procedure highly depends on our assumption, right? I mean, this is kind of the flavor of mathematics, really. Whatever you assume, you must follow consistently. I assume sigma is known here. Therefore, it's legal for me to use this as a pivot random variable, because if I pivot, right, it will ultimately lead to the consequence that my left and right point depends on the parameter itself, right? This sigma right here comes from this sigma here. But if this sigma is unknown, again, I hope the midterm 1 kind of brings it home for you, then this is nonsense. Yes, I mean, you form a confidence interval where the confidence interval involves an unknown parameter. What are you talking about? But of course, here sigma is known, so everything here is legal. That's all I'm trying to say. All right. So one last thing I want to say, right, is maybe there's another similar question is how to find pivot random variable. And this is usually the harder question, right? A statistician would actually have to look at this question really, right? As you can see, these are, like I said, if you're given one, then you know by 1, 2, and 3, you know whether or not it works, you know, or not whether or not it's legal. Right here, though, is the one, right? How to find. And let me say this, right? The pivot random variable, for example, how did we find mu hat pivot here? A lot of the times, and most of the times, I would say always, but you know, when we say always, is like as a this is empirical rule, so I cannot say always, but most of the times, theta hat pivot comes from the normalization of an estimator theta hat of theta. Okay. So the steps of finding pivot random variable can roughly be put like this. 1, find theta hat for theta. Find an estimator. 2, normalize theta hat so that the distribution after normalization does not depend on any unknown parameters. So what is it? This step 2 right here is exactly landing you on step 1 of the theta hat pivot. Okay, because that known distribution is exactly from the normalization of the theta hat. Okay, so for example, x1 up to xn, IID, normal mu sigma square. Well, suppose you want to find confidence interval for mu. Okay, that's your question. Where you start? I mean, I guess by now you think, okay, what's the pivot random variable? That's a good question to ask. But you may realize that this is a little bit harder question to ask because it requires you to jump 2 steps. The first question to ask rather is, what's an estimator for mu? Okay, what's a natural estimator for mu? And I think, right, by now everyone would agree that mu hat is x bar, right? But obviously, if you glance at this, you see that this cannot be a pivot. So this works as an estimator. By the way, right here, let me spell it out again, that we are still in the context that mu is unknown, of course, because we're looking for it, but sigma known. All right. So mu equals to x bar works as an estimator for sure. I mean, mu hat is completely known, but is not a pivot random variable yet. Okay, why so? Because the distribution of mu hat is normal with mean mu and variance sigma square of n. So it violates, right, this requirement right here. Well, technically speaking, right here is the most violation. This point you can live with because sigma is known. So, but like again, in practice, any parameters, any population parameters should be assumed unknown. So actually, this is anyway, right? But right here, so this is why to get to mu hat pivot, you must normalize mu hat. But what's the normalization? Well, I think everyone knows that it is subtracting mu and divided by. Is that okay? So that's the logic. That's how you come up with this. And then, of course, you put that into the probabilistic statement, and then you pivot, and then you get your confidence interval. Any question? So now suppose that you want to find confidence interval for sigma. This is 11.4 whatever, right? But as I mentioned, the sections after this 11.1 are just really decorations. The main idea is already here in the pivot random variable. That the 11.4 doesn't mean it's any harder than 11.2. So if you want to find confidence interval for sigma square, where do you start? How would you do it? First, what do you do? Yeah, and what is the estimator for sigma square? Very good, right? So S square is sigma hat square. Is this a pivot? Not yet, right? Not yet, because actually, if you have studied for the midterm, you probably have gotten this by now, right? What is the distribution of S square? Actually, we don't have a distribution for S square, right? We have a distribution for is normalization, right? So the normalization is n minus 1 S square over sigma square. Agreed? And chi-square n minus 1 is free of unknown parameters. Okay, you're almost there. Step 3, pivoting. How would you pivot this? How would you pivot this? The pivoting step actually is very mechanical, right? You just take whatever the pivot is and you slap in the quantile. So something like this. okay? Where, again, these are the population quantiles. So I don't know. I mean, this may look like a chi-square density. Then, right, these are 2 points. Easy, okay? And I'm being sloppy because I need to throw in the n-1. Otherwise, I'm not completely identifying my chi-square yet. Are we okay? Any question? You know why I call this 1 minus alpha over 2, right? Because by our convention, the quantiles always refer to the right tail quantile, okay? I don't know why, that's just the way it is. So therefore, right, by this, I mean the area to the right is 1 minus alpha over 2, which means the area to the left is, right, alpha over 2. There's no negative stuff going on like the normal, right? Because the chi-square density is not symmetric, right? The chi-square support is on only from 0 to infinity. So here's where like some basic knowledge, right? This is like basic knowledge of chi-square density is important. Like you don't need to know the exact shape of this chi-square, I think, for this kind of working things out. But if you do not know that it is from 0 to infinity and is not symmetric, then you'll very easily get something like this wrong, okay? But this is the way you write it. Then, of course, comes the act of pivoting. But the act of pivoting, again, right, is easy. You just somehow try to put the sigma square in the middle. Well, what would that be, right? So that would be n-1 s squared divided by chi-square n-1 alpha over 2 less than sigma square less than okay, so that's the act of pivoting. Therefore, your confidence interval for sigma square is your a confidence interval is this and this, right? Okay. We say is a confidence interval because there could be others. I mean, still based on the same pivot random variable, right? And how do you find others? How do you construct others? How would you construct other pivot random variable? Sorry, how would you construct other confidence intervals based on the same pivot random variable? You would do that by playing, right, with this choice of alpha over 2, because you want it to be 1 minus alpha, right? But there's no reason why you have to split this to be alpha over 2 and alpha over 2. Just the same as with the normal example. You can split this into P1 and this into P2, where P1 plus P2 is alpha. Okay, the choice is yours. So for example, you can go to the extreme and put this to be at 0, meaning, right, this is 1. So you choose no left point. So this must be the whole alpha. Or you can go to the extreme and push this to infinity, right? So there's no value here, this is 0, then this must be 1 minus alpha. Or you can shift, right, things around somewhere. Okay, so that's an easy point that I won't repeat anymore. So the standard one is this, right? The standard one always try to split half and half. Now in the normal case, you know why that is, because the length of the confidence interval when you split half and half is the shortest. I'm not so sure about this because symmetry is no longer there. It might feel optimal, who knows? Proving that it's optimal here in the sense that it's shortest length is not easy, and in fact, I'm not sure it's the shortest. But anyway, right? The convention says why not do half and half? It's just symmetric there. Okay. Any question? Great question, Alice. You could just send a message to a class. I think the class would like to see your question too. Maybe you just missed. So Alice was asking, are pivot random variables all unbiased? I don't think so. It's a good question. It's a good observation because you see it from here, right? That they're unbiased. I don't think so. It doesn't seem connected. It seems mostly there, but it's unclear that they're all unbiased. I don't know. It seems like that, right? But you see, logically, there's no reason why we require that. Your empirical observation is correct. That means I have, quickly going through the ones I know, they seem unbiased. But logically, I don't see any reason why we have to require it to be unbiased. What we require, right, is that the distribution of the pivot random variable to be free of unknown parameters, to be free of parameters, right? But somehow I think the natural normalization brings it to unbiasedness, but that's not logically required. All right. Any other question? So in connection to this, all right, let me discuss your homework of this week and show you how the idea here applies to your homework. So for example, your 11.1 says this. So x is an exponential lambda, and you have only one sample, sample size of one, only one sample, one member in your sample. All right. They ask you to find k so that the book has a very strange language, right? I mean, 0 to kx is a 1 minus alpha confidence interval for lambda. Okay, they call it theta anyway, doesn't matter. But all right, so first of all, what are they talking about here? First of all, right, what is the probabilistic statement behind this? They just write as English, right? What is the probabilistic statement behind this? So the statement they want, right, is find k so that probability of, I guess 0 doesn't matter, right? Because lambda is always positive anyway. Lambda less than kx is equal to 1 minus alpha. Yes. And obviously, because you know what x is exponential lambda, this is a very easy problem. I won't even comment on it. But the reason why I bring it up is because here, right, it might seem a little bit out of sync with the discussion, right, of the theme, right, of how we approach things. So let me bring it back, right? That the reason what I want to do here is bring it back, bring this question back to the idea of pivot random variable and show you how, if you see a pivot random variable, then this is a very easy question to do in a different way. So again, right here, I hope that mechanically, you don't even need to understand confidence interval, right, to solve this question. Once you can put down this probabilistic statement, then you can just do it mechanically. Okay, but I want to bring in the concept of construction of confidence interval here. In what sense? Suppose you look at this, right, and you do this. What are the steps that we would go through to construct the confidence interval for lambda here? First, estimator. What would be an estimator for lambda here? What would be an estimator for lambda here? Good, but because n equals to 1, what is x bar? That single element. No. N equals to 1 doesn't mean, right? N equals to 1 means you have one element in your sample. X1 if you want, or X, right? Is that okay? Yeah, X, right? You have one single X. That's why you don't even bother indexing it. It's just X. Okay. Okay. Is this a pivot random variable? Is it a pivot random variable? Exactly, right? Not yet. Why? Because obviously its distribution depends on lambda, where lambda is unknown. Now, how to do the normalization? There actually, if you don't have an experience in probability, you may be a little bit, you think about it, right? But okay, let me say this, right? What is the natural normalization here? Hint, right? The book does this. So what direction do they want to normalize? There are two ways to normalize only. I mean, in life, there are not too many ways to normalize. Scale, meaning divide, multiply by a constant, and location, shifting, right, by plus minus. For example, you see normalization of mu is essentially a location, recentering. Normalization of sigma square is a scale. So which case is this in this case? What is the normalization? By what? By what? No mu here. Lambda. Is that what you're saying? By lambda? So what is the scale? Tell me. No. K. So forget this K here, right? That's why I say K is a little bit strange. But this K right here is the unknown thing that you look for later. For example, you see, essentially the scaling, right, is this to get to pivot, the normalization. But later on, you get some declaration with respect to the chi-square score. So do not confuse K with lambda, all right? K is the part that depends, that goes into construction of confidence interval. We're asking for normalization of your pivot random variable to get to your pivot random variable. K is unknown, by the way, at this stage. So not K. You're being too mechanical, Madaf. You're using the normal the z normalization, right? But does x have a normal distribution here? No, it's fine. It's fine. It is not. I'm not criticizing you to be sorry. I'm criticizing you so you be a bit. Yeah. But right, try to see what we're dealing with. Otherwise, you'll be very fixated on the formula, then you won't get it. By lambda, what do you mean by that, Derek? You're almost there, but what do you mean? So what is it? What's my pivot random variable? Lambda hat is x. So what's lambda hat pivot? Let me give you a hint, right? What's expectation of x? What's expectation of, what's variance of x? Yeah. What's the natural pivoting? What's the natural normalization? X over lambda. Do you see that? Because what's lambda hat pivot? What do you think its distribution will be? What do you think its distribution will be? Exponential what? Exactly. Now, of course, right, this statement needs proof. How would you prove this? No. MGF of exponential is a bit, I don't know. I don't know that by hand, right? But if you look at the solution to 1A of midterm 1, that's how you do it. It's very simple. It's just a change of variable in your PDF, right? Okay, let me show you. You want to prove, right, probability x over lambda less than or equal to x, right? Because that's the CDF. That's the CDF of this random variable. Okay, this is a CDF of x over lambda. If it were bona fide, right, a exponential 1, then it should be this. Agree? What am I saying? Right? If this is true, then this is exponential 1, because this is the density of exponential 1. Are you okay? But of course, what do you do here? You know x is exponential lambda. You know x is exponential lambda. So you convert that, right, into, you convert it into, right? So this question mark is what you wish for. You convert it into this, and then you use the known distribution, which is right. But of course, to go from here to here, what do? So I even do it, make it easier for you. Let me say V here, right? What's your change of variable? Correct. Question? Okay. So you see that once you recognize a normalization going on here, you can even work with the book. Who cares? So they want to do this, right? They want to find this. But so you see somehow this, you see why this K right here suggests a normalization, even though it's not exactly the normalization constant. What would you do here to convert this statement into something that we, in light of what we just discussed? How would you convert this statement into something that we just discussed? Well, you would normalize everything with lambda. Right? Sorry. Okay. Like this. Now, then that would be, oh, sorry. So what's wrong with my, so probability, right, that 1 less than k x over lambda is 1 minus alpha. Okay. And x over lambda has an exponential 1 distribution. So ultimately, you do this. And there you go, right? That would be the integral, right, from 1k to infinity of e to minus x dx is 1 minus alpha, and solve for k. Is that okay? Now, again, I know that all that I wrote here, right, the normalization step is an overkill for this problem. But when you solve this, I hope you realize that, right? Normalization by multiplying by a constant is the implicit idea here. If you see that idea, then you see the non-mechanical approach to this problem. Otherwise, right, you just kind of solve for it, kind of by formulaic approach. Question? So to make it less trivial, right, let's look at 11.2. 11.2 tells you this. Now they want n equals to 2. They say x1, x2 are IID uniform 0 to beta, right? And they want to find k so that probability of 0 less than beta less than k times x1 plus x2 is 1 minus alpha. And they have the mysterious question where, you know, they say, let's say alpha less equal to 1/2 in part A and alpha bigger than 1/2 in part B. Now, let me tell you, right, this question, if you don't know what the direction of thinking is, even if you try to solve it mechanically, it'll be a very painful question to solve. There's still some probabilistic knowledge at the end that you have to know. But, okay, Do you appreciate why this question, if you want to solve mechanically, is not pleasant? What do you need to do to solve for this question? What do you need to do to solve for this question? Join PDF is easy. I'll tell you that. Join PDF of what? Of this? Because they're independent. It's just 1 over beta square. 1 over beta square. X1, X2 less than beta. That's not hard. Yes, you need to join PDF somehow, but that's not the point even. What do you need? Obviously, you need the distribution of X1 plus X2. Okay. Now, does anyone know what that is? When you sum two uniforms, what do you get? Exactly. It's a triangular distribution, but where does a triangle go? How does a triangle behave? In this case, from where to where? So, okay, we'll have to use a triangle at some point, okay? But for now, let's just go back to our way of thinking. So our way of thinking, right? If you want to find beta, all right, the first thing you do is, what is an estimator for beta? What is an estimator for beta? And looking at the book's question, right? What estimator are they aiming for? What's an estimator for beta here? Exactly, right? 2x bar, exactly. 2x bar using the moment method. And 2x bar here is x1 plus x2. Okay. Is this a pivot? Yeah, I think it's safe to say not yet, right? But I hope you see why, because these guys depend on beta. So fine. What is the normalization step? What is the normalization step? You only have two choices. Yeah, scale by what? Scale by what? Well, pay attention to the population distribution. It's uniform 0 to beta. How would you normalize this uniform? Exactly. So the normalization will be x1 over beta plus x2 over beta. Or, of course, it's this anyway. That's your pivot. Look at this statement. Is it hinted at for you that that's the normalization going on? Look at this. Do you see that normalization staring at you? So this would be probability of 1 over k less than x1 over beta plus x2 over beta is equal to 1 minus alpha. Okay. So now this is uniform 0, 1. This is uniform 0, 1. Oh, did I do something wrong? No, that's it, right? Yeah, 1 over k. Yeah, that's it. So now then, right, you still need to know this distribution, but go back to what Madhav said, right? It's going to be a triangle, or go back to the question, how do you sum two independent uniform 0, 1s? What do you get? You get a triangle from 0 to 2. What's the height? The total area must be 1, right? So base times height divided by 2, exactly the height square. So then what is this question asking you then? So it's asking you to locate 1 over k, right? 1 over k is somewhere here. So that what happens? So that the area to the right is one minus alpha. And this can be solved geometrically. You just look at the area. So by the way, right, that means the area to the left is alpha. And now you understand why they divide into 2 cases, right? Because if you happen to land it here, then this is 1 minus alpha. And the geometry is just kind of, inverted. There's nothing really difficult there. But of course, right, this is the case when alpha is less than a half, right? And this is a case when alpha is bigger than a half. Am I wrong? Hold on. Yeah. Any question? So the point, right? I'm showing you this is not to solve your homework for you, but the point is I want to direct you to the idea that, right, in a very mechanical question of the book like this, looks a little weird. But once you realize the idea is there is normalization going on, and you know that you must look for normalization coming from the pivot random variable, then you will naturally do something like this. Sorry, something like this. Okay, or something like this, which would make your life much easier, because after you normalize, right, then things don't depend on that parameter anymore. You see, the beta drops out. The beta drops out of consideration here. The lambda drops out of consideration here. Again, not that the original question is that hard to deal with, because in some way, the book did give you the pivot random variable in a way, the pivot structure. They did give you the pivot structure by asking you this statement. But I still claim that without realizing that's the pivot or what the pivot is and what the normalization is, your calculation will be unnecessarily painful. Because it's your homework. What do you mean? Why do what? I'm joking, but what do what? Yeah, you know, at the end of the day, right? It's just make your life easier. So I bet that you haven't tried this problem, right? Which is fine. I'm not trying to say that you have to do this problem now, but without trying this problem fresh, meaning haven't had me telling you what the approach is. Or if anyone in this audience have anyone tried these problems by themselves before, and if you don't mind telling your experience, especially with problem 2, I'd like to hear, because my experience is the average student in this class have a hard time with problem 2. Am I wrong? Did anyone try this? So Derek, right, the answer to you is, it's hard for me to tell without you solving the question. It's like I told you the map already, so you say, okay, what's the point? But if you struggle with it, then you understand what the point is, right? The point is that the normalization structure makes everything natural for you. So maybe that's why you think it's a dumb question to ask, why, you know? But without recognizing that this is the ingredient, you'll be circling around this question for a long time, as my experience tells me. No problem. Yeah, right. At the end of the day, I don't know. I mean, you can see from my midterm to the question in this book, right? If you look at it the right way, then there's not much to ask. The questions are very easy. But again, right, glancing at the midterm results, I can tell that a lot of you struggle with the question because it just, you don't look at the right direction. And I get that, right? That's hard. But that's, if anything, that's my message, that there is the right way and the not so right way to look at things. The right way makes everything natural and fall down to your lap. The unnatural way of looking at things may not even solve the question to begin with. All right. And I try my best to show you what the natural way of thinking is, I hope. Okay, any other question? All right, so. All right, so now let's move on to the other, right? So now we're done with pivot random variable. So let's move to the case when, right? So now we go back to the case of the normal distribution. And assume, right, that both mu sigma are unknown. Okay, this is the case of interest. Now, if this is the point, then x bar minus mu divided by sigma over root n is no longer a pivot, because sigma is unknown, right? So what is our pivot? So now, even without, knowing advanced statistics, not too advanced, a very easy, intuitive thing to do is whenever you have unknown parameters that you want to get rid of meaning, not having it there, not like canceling it, then you just replace it with its estimator version. Okay, so a very trivial thing to do here is to do this. Replace sigma with S. But of course, right, the hard thing is, what is the distribution? Okay, and you hope that it does not depend on sigma and mu. Okay, because just because you replace something with its estimated version, so doing this solve one thing, solve the problem of sigma unknown, but it may create other problems, meaning you may drag it into the distribution somehow, right, without you knowing it. So anyway, right, when you come up with this as a potential, right, this is a candidate, okay, at this stage, it's just a candidate for the pivot random variable. Until you check that the distribution here is clean, is independent of unknown parameters, then you cannot say that confidently that it's pivot, okay? But so this is the hard work. In the case that you have to deal with a completely new problem, then this is also a potential question you have to deal with. What is the distribution of your potential, right, pivot random variable? And by the way, this is exactly the point of this question in the book, right? This is your pivot. What is its distribution? That's exactly this question right here. This is your pivot. What is the distribution, right? This is your pivot. What is the distribution? Okay. Now, of course, here it's easy because you see also why, right? The book likes to ask questions with sample 1 and 2, because with sample 1 and 2, you can explicitly write down what the distribution is. When the sample size is n, things are hard, right? That's why we need, not hard, but things are tedious. So that's why we can only do some generic result with some generic distribution. Anyway, right here, the answer is, of course, the famous T distribution, right? Tn minus 1. So the point is to show why is a Tn minus 1, or what is a Tn minus 1, right? So question is, what is Tn and why, right? But so that's the question that we should address. But let me show you, right? But after you got this, suppose that you accept everything like this, and Tn minus 1 is clean, meaning it does not depend on any unknown parameters, kind of by its notation too, right? Because you only need n minus 1 to describe it. You only need n to describe it, like chi-square. You don't need any mu sigma, right? Because, and that's why I keep asking, right? Yeah, you students like to tell something like, oh, is it uniform? Is it exponential? You should realize that by saying that, you only say half of the answer, because uniform what? Exponential what, right? This always depends on parameters. So if you follow the convention, then, and if this completely describes everything, then T does not depend on any other parameters, right? Only n minus 1. So anyway, right, we will address these questions soon. But if you have this, then you see the pivoting step is very easy. Accepting this, pivoting, right, is straightforward. Well, assuming that what is Tn here, you will discover that it's also symmetric. It's like it's almost like bell shape, right, with a fat tail. But anyway, it's straightforward because I will quote this, symmetry. Because the shape is exactly like the normal shape. So the symmetry in the normal also works here. And then obviously, right, from here, I know that x bar plus minus t n minus 1 alpha over 2 s over root n is a 1 minus alpha confidence interval from mu, in the case when sigma is unknown, right? So the pivoting steps is exactly like the case of the normal. And this is why I do know, right, that you guys are not no stranger to the T distribution and to the S, right? If you have taken some elementary statistics or in other courses. So you see the formula right here is very mechanical. It doesn't tell any story, right? You can even teach like a high school student that, replace Z with T, replace sigma with S, there you have it. The hard thing, right, or the more mature thing to do is right here. What is Tn? Why this, right? Know the what and the why of your application. Application straightforward. Okay. So any question? Okay. So now let's go with the what. Now, this what is in a very similar spirit to the chi-square. I did say, right, that a random variable is completely described by the density, right, among other things like the CDF or the MGF. But in this class, in statistics, it's very cumbersome to describe a random variable as a density. We will still need to know its density a little bit to know its properties. But the definition, right, the working definition almost always does not rely on density, right? It relies on distributional definition. In other words, Tn will be a standard normal divided by chi-square n over n, where these guys are independent. This is the working definition. Okay. So in other words, if you have an two independent standard normal and chi-square n, you form this ratio. That's the T. Okay. This is in the same flavor, right? I hope you know by now that chi-square 1 is standard normal square, and chi-square n1 plus chi-square n2 is chi-square n1 plus n2 as long as they're independent. Right? So this approach, again, is a distributional approach, right? This distributional definition. Behind this, somehow we still need to show the density a little bit. But right, when you're working with problems like question 3 on your midterms, you will never really want to go back to the density level, right? So here, this is the definition. We will show the density, right? Maybe not today, then next time, because we may not have enough time. But so after I show what, then I need to show the why, right? So the why here may surprise you a little bit because it may surprise you a little bit because you see, this is like root, right? This is divided by root n right here. But here is root n. Why is it n minus 1? They are making a mistake. Maybe this is Tn minus 1. What's going on? Okay, good. That's exactly it. Very good. But then okay, that explains the n minus 1 maybe. But then so why this is Tn minus 1 in view of this? So let me ask you this, right? Is this standard normal? Don't be too quick. Is it? What distribution is this? Well, let me ask you this. What's the variance of this? Yeah, of just the numerator. Actually, the variance of this actually is not easy, all right? Even if, yes, it's sigma squared over n, because I have not normalized the x bar in terms of scale. So therefore, right, Samuel, this cannot be standard normal. So that's actually the clue to the missing question, right? This is not in that form yet. You don't have your standard normal. Similarly, you do not have your chi-square n over n at the bottom. So the proper structure is this. Okay. So two things. First, do you see that algebraically it cancels out to this? And B, right? This is your standard normal, and this is your chi-square n over n. Sorry, chi-square n minus 1, right? So this is standard normal over chi-square n minus 1 over n minus 1. And that's why it's Tn minus 1 in view of this. And because the sigma cancel, the n minus 1 cancel, you get this. One final thing though, and this is still subtle. Why are they independent? Because you require independence too. Why are they independent? This is that result of x bar and s square are independent from a normal sample that we set once upon a time when we discussed chi-square. We did not give a formal proof of this because it relies on some properties of the bivariate normal, which is within your graphs, but we did not cover it. So we just say that you accept this. But you see how many ingredients go into constructing your T, which everyone use so casually. The independence, the chi-square structure, and the cancellation. And by the way, right now, let me go into the canceling structure. It's very beautiful here too. And I hope you appreciate this. This is not standard normal. It's standard normal when you scale it with an unknown constant sigma. Okay, remember sigma is still unknown. Sigma is still unknown. Okay. So, but of course, you want to scale it anyway. Otherwise, how can you get to a standardized version? But the point is that when you scale the top, you use exactly the scaling factor for sigma at the bottom. So therefore, these two scaling factor, even though you use them, they cancel out. And that's why your statistic becomes independent of sigma. All right. So that's the beauty of it. That's why it's a big deal, right? That is the same scaling factor that works on top and bottom, allowing you to cancel out this, mysterious sigma, getting you two things. First, your statistics is free of sigma, but the distribution is also free of sigma, so you can use it. All right. Any question? Okay. So finally, I just want to show you the simulation. This is the same program as we talked about last time. Okay, so the first one, remember, is just showing you the concept of confidence intervals, right? What it means. So here I form 10 confidence intervals, right? From a sample of size 10. So let me change the sample to size 9 or size 8, doesn't matter, right? So the size is the different things from, right? So right here, right? I form 10 confidence intervals. And you see, I have one, even though the alpha is 0.05, I missed the coverage of 1. All right. So here, when sigma is unknown, so this is the case when you use a t distribution, right? And right here, right? So looking at this, you don't see them to be very different. Okay, looking at this, you don't see them to be very different. But here, I will compare the z and the t for you. And what you should recognize is this. Whoops, sorry. That the t confidence interval tends to be larger than the z confidence interval. Same, right? Same level of coverage. Same level of coverage, right? Well, I guess it's not true, right? Why is this smaller? That's weird. Hold on, let me try again. Did I get it wrong? Oh, 2 t stat. Yeah, it tends to be larger, but of course it's a random effect. Last time it was smaller for some reason. Tends to, right? These things are random. When you see it tends to be larger. Why? Because the T is more flat, it has a fat tail, all right? It has a fat tail. So the fat tail effect requires you to go to a bit larger. But also you can argue that because sigma, you don't know sigma, there's some randomness. You have to go out further to catch the same coverage, right? These are both coverage for mu. But if sigma is unknown, you need to go out further, right? To catch that, to account for the randomness of sigma too, okay? Intuitively. But mathematically, the fat tail, the fact that t distribution decays slower than the z distribution makes this. All right, so they are different. Okay, that's what I want to emphasize. They are different distribution. They are different confidence intervals. And here, right, to show you the asymptotic coverage rate, meaning that, right, the point is when you really simulate a lot of intervals, then you get the coverage rate to be similar to what your alpha is, right? So a 99% confidence interval has this coverage rate. This has this many coverage rate, right? But let me show you, right? This is where I use the z confidence interval when sigma is unknown, which is wrong, right? Meaning, what do I mean by that? What I mean is instead of using the t score, like the t quantile, I use a z quantile. Right here, I use the z quantile. This is norm, right? I use a z quantile. Then you see that the coverage is not 99%, it's less because you use a smaller confidence interval. All right. So in other words, you definitely need to use a t quantile, the t distribution, even if you replace sigma with s, But if you use the z quantile, right here, norm, not t, right, then you will miss coverage. You will not cover as much as you think. So in other words, right, you need to use the t distribution, and that's why. All right. Can I change alpha here for you? Let me change alpha to 0.5, right, and show you the same thing happens. You see, right, they cover slightly more, but it's roughly 95% when you use the z distribution and the t distribution. But when you use when sigma is unknown and you use the z distribution, you are definitely undercovering. All right. Now, this is because the sample size is small. Sample size is 9 or 8, whatever. When the sample size is large, all right, then the z coverage and the t coverage are actually roughly similar. So can I change this for you? let's say n equals to 100, all right? You see, they're roughly similar. And if n is equal to 100 here, the coverage are similar, all right, even if I use the wrong one. So there's that idea that the t distribution converges to the z distribution, the normal distribution, when the sample size is large. But obviously, right, when you are dealing with small sample size, which a lot of times you're dealing with, then, right, knowing the exact distribution is very helpful. Otherwise, you undercover. And that's the point of MathStat, all right? You figure out exactly what you're doing so that you do the right thing. Okay, so next time we'll go over the density of a t distribution, all right? Thank you guys for coming. If you have any question, I'll answer. You too. Thank you. I did. So there are two places you can find, either in Zoom recordings, which I assume you went to, or on the course modules. There's also a link to that. Sometimes I forgot to open the Zoom, but I always post, the link to a course module. So I would also open it. I will go back to Zoom and check. I assume you're referring to that. But the course modules, they're always, the recording. So yeah.